So officially, good morning for those of you that will watch this on the recording at some point. I'm just was talking in class before I started the recording, and I'm on the website right now just pointing out that late last night I finished doing the install on my tablet of the Julia Python Jupyter Lab Pi Audio installation document, or following my document. I had to make a few additions just to clean some things up, but it went on smoothly, and the fruits of my labor are right here in the sense that this is running locally. It's not running on my subsystem for Linux set up on here. So this is exactly what I had talked about, and if I go over here to PowerShell, this is exactly what you're going to see. I'm going to bring the system down in a little bit and then open it back up again, but this was launched right from the Julia prompt, just like I was talking about last week. So once that happens, you don't pay any more attention to this. Error messages and other dialogues might come up, and when you get ready to kill this, you go Control-C in this window, but you don't do that until you've actually shut the Jupyter or closed this tab over here. Things that you probably don't realize, but what these tools now do is they actually run a local web server. So you're running a web server right on your machine that you're connecting to, and then it's talking to the kernels, the numerical engines for Julia and Python, and that's what this tells you, that you've got that capability. And I put on 1.8. That was mine. That's the latest release that came out a week or so ago. This is an earlier one that I apparently never got removed, and it's still available, so it says, but these two are the ones that we'll be able to talk about. So I'll say more about that in a little while. Before I actually launch into Chapter 2, I want to just see if there's any questions on anything. Obviously not everybody's here, and if some people don't show up today, I'll assume that they're not going to come ever again, but there was one guy that never showed up last week, but I'm not even sure if he's in the country or not. His name is Omed, and he was going to be a student of Dr. Omed Semiari, who is the guy who resigned in the middle of the summer. So I'm not sure that he's actually came from Iran to the United States. Does that make sense? Because I kind of think that's a possibility. He was the only one that wasn't here last week. Jack is not here. And Cooper is not here right now. Okay. I do have solutions with me today. I've got a hints page that will be going up a little bit later. Let's just take a look at how I rectified that a bit. Oops. I just said hints will be posted soon. I cleaned up the old links that were on there, and I've got the hints page ready to roll up there. I'm probably going to put it up this afternoon, but we'll be able to talk about any of the problems as we move on to the lecture material. I've also relabeled this Python and Julia, and the stuff that I have links for on the home page relate to this material right here. I now have a zip package that has two set number 1 demo hints notebooks, one for Julia and one for Python, but those are listed right here, same exact link, and then the PDF version, so you can just look at those if you want to see what the hints and techniques are in the two different programming languages. And then I moved the packages that the modules I've written and put into a zip package over here. It's just modules that are useful when using Julia, because right now Julia doesn't have a mature base of code. It has lots of nice packages, but I want them to be easier to use for everybody. So that's what I started writing actually 2 years ago when I was on my sabbatical, when I first started getting interested in Julia. So with that said, about 2 years ago, it doesn't mean it takes 2 years to learn the language. It just means I had to sit there and think about what can I do with this? Is this going to be fruitful? Sort of get the pulse of the community. And honestly, they haven't produced any better tool sets, but Python was the same way when I started with it. It has a nice package, scipy.signal. It's gotten a little bit better, but still by writing the functions that I did in my module, it wraps things up and makes things, I think, easier, especially for teaching. And we can use that in both Julia and Python. So whichever way you want to play around with it. So getting started, I put a battery in my pen so it works again. I think whoever developed these pens, and it's the same when I had a Surface Pro, and this is a Dell pen. This is a quadruple A battery. Has anybody ever worked with one of those with any gadget you have? You know what or no, maybe it's a triple A. It's a triple A battery. Double A is, A batteries and double A are pretty popular, right? These are really, really tiny batteries, and of course, they're expensive. And they fit just in the diameter of this pen, and they don't last very long. So I have a package in my bag. I just didn't want to get it out last week. I'm not on a web browser, but if you were browsing this live or I downloaded it, these would all be links. But on this tool that I'm using to write on, I don't have the links working. So signal basics is what we're going to go over just to get into this quickly. And this also reviews through things that you've seen before back in your days of taking Signals and Systems 1 and 2. That would be 2610 and 3205. Some of you probably took 3205 1 year ago this semester, right, with Dr. Trimboli. So that should be your freshest remembrance. This just extends off of both of those classes, though. So we're going to be dealing with one-dimensional signals, and a signal is just a function of one or more independent variables. But then we have time as one of the free-running variables within the function, and I'll explain that more in a few minutes here. We could also just as easily be working with images, and they would be 2D signals, so it'd be usually space, but it could be time and frequency. It could be just two other independent variables. And then getting into specifics of how electrical engineers view this, we view it as either continuous or discrete for these independent variables. If we're thinking about the world that we live in, and I'll just use a simple example of when I'm speaking, my vocal cords through my cavity in my throat is producing a sound pressure wave that is radiating out into space, and that sound pressure wave disturbs the molecules of air, right? I mean, you've heard this in physics. If it sounds like physics, it is physics. And then it arrives into your ear canal, and then your tympanic, what's it called, nerve or whatever, at the end of the ear canal, receives that pressure wave, and then it gets converted into some electrical stimulus for your nerves, and then your brain, you know, that's just a mystery exactly how we all interpret the sound, but it gets converted back. So it's going from a pure mechanical means, air past my vocal cords, all the way into your eardrum, and then it becomes a signal that arrives at your brain. If we were doing this like my recording now, it's still a sound pressure wave, but there's a transducer in the microphone which converts that to a continuous time signal, but then there's an analog to digital converter running inside my laptop, which is converting that to a discrete time one-dimensional signal. I'm just trying to paint the picture that we have signals in various mediums, and then they go through conversions, and they go from continuous to discrete. And in the case of playing back, you're going from discrete back to continuous if you're listening to a recording, and so on. So We do live in an analog world, that's my feeling. I believe even the brain transfer gadgets that people are now experimenting with are working with analog signals. They're not working with a digital signal per se. But on the computer, we work with discrete time signals. So with that said about, get the right pen up here. With that being a discrete time signal, then there's this. What's the difference between a discrete time signal and a digital signal? Because most people say DSP as in digital signal processing, but yet the title of the book has on it discrete time signal processing, right? What's going on there? It's just a fine point. Discrete time signal processing is just putting an integer axes and putting sample values on the integer axes. What are those values? In the book, mostly, those discrete values are real numbers or complex numbers with infinite precision. When it's a digital signal, though, like stored on a computer, then it's got a finite number of amplitude values, so it has a finite word length representation. It might be a float 16, a float 32, a complex 128, 64 bits in both the real and imaginary parts. So we make that distinction is made in the book, and eventually we will talk about random processes and modeling of quantization and the finite precision effects. But most of the time we'll be working with almost real numbers. I say almost because on the computer, MATLAB uses double precision, which would be a 32-bit real. You could go to quad precision, which would be 64. And then there's 16-bit floats. And then there's like int 16, which is a signed 16-bit integer. There's int 32s. I mean, all these other things that you can find in all of the modeling languages we have. Python for sure, Julia for sure. I don't use MATLAB hardly at all anymore. I'm pretty sure you can create the different types in there too. So discrete time system, discrete time signals, input and output, digital system, both input and output digital signals. I'm not really going to be that picky about it, but it's just so you understand that there are differences, and precision is a factor. I was just thinking about software-defined radios that I have. One of them, the RTL SDR, which was used in the COM lab last spring, it only brings in samples at 8 bits. In phase, which is the real part, quadrature, which is the imaginary part, are just at 8 bits. I don't know if it seems like, how can you just get by with 256 levels of amplitude, which is what you have with 8 bits, but if it's oversampled, and we'll be talking about that eventually in the chapter on sampling theory, what it means to do multi-rate sampling, and then what can we do to improve the accuracy through other techniques like oversampling, and something that we'll talk about too is called the delta sigma A to D. Delta sigma is a technique that was developed quite a few years ago now to take a 1-bit A to D converter that's oversampling and produce 16 bits of resolution out of it. Does that seem pretty special? I mean, I say special because a quantizer that only has to quantize between a +1 or a -1, but if it's oversampled, you can actually fill in values in between and go up to 16 bits of width. And that's is what the delta sigma revolution, I'll call it, of A to D converters brought on the scene quite a few years ago. So again, 1D discrete time is our mainstay, and then occasionally we'll be doing some finite precision numerical effects. So now the next topic is signals as sequences. Electrical engineers want to think of it as a signal, but if you're a mathematician, you would be probably referring to it as a sequence. So then they would like to use a pure math person and go, I'm taking you back into calculus when you first learned about sequences and series and geometric series and the ratio test and for convergence and all that kind of stuff. You probably used a notation like this. It was just a subscript. And you might remember that the harmonic series, well, do you remember the harmonic series, maybe I should say? Remember that from calculus? That's a sequence that follows the pattern of 1 over n. So you're going to go 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. Do you remember that that one doesn't converge? Vaguely, I mean, you probably remember that. Whereas 1 over n squared does converge, for example. So another alternate notation is this guy, but then the one that our book favors is the square brackets. And if we're dealing with a continuous time signal converted to a discrete time signal, this might be the notation. So the book will frequently use A for analog, and then parentheses to say it's a continuous time signal, and then replace little t with n times capital T. And we'll major on that when we go into sampling theory. One of the things that I've said all these years that I've taught this class, though, that I use to remember, and maybe is the reason why the authors chose this notation, is the parenthesis for the continuous time signal is smooth, so it's like it's continuous because it's got curvature to it. And the discrete time signal is a square bracket, meaning that it's got sharp edges on it, but that's not strictly the case. It's just meaning it's discrete. It doesn't have a smoothness to it. That's my artistic interpretation. Do whatever you want to with that, but I'm saying that because some textbooks don't use a square bracket. They'll just put an integer inside the parenthesis or a time inside the parenthesis, and you just decide based on that. But this book uses the square brackets. And we'll learn about sampling theory again or revisit that. But if we have a continuous time signal and then we sample it every capital T seconds and let multiples of capital T be represented, correspond to the integers, then we get a discrete time signal plot. And in all of our programming languages, we have something called the stem function, which creates these types of plots. A long, long time ago when I first started teaching this was also called a lollipop plot. I don't think that term is too popular anymore, but it was like a sucker that you would lick, right? And it would look like these are a bunch of lollipops along the axes. That sounds really weird, I know, but they used to refer to it as that. The importance of using the stem plot versus just a plot which would connect the dots is that you can't really display a discrete time signal properly if you connect the dots, because there are no signal values in between the integers. Is that clear? However, when you're plotting a discrete time signal that's got lots of points on it and you try to plot it with the stem function, it takes a while, and it just is a huge mass of these dots with these stems, and it's not all that useful. So generally what I would do is just do a regular plot where it connects the dots together. But the idea of connecting dots would be simply linear interpolation if that's how you choose to connect the dots, and that's a special type of signal processing operation that we'll talk about when we do upsampling followed by an interpolating filter. So it's not legal to say there's values in between those samples in a discrete time signal. They're certainly not stored on the computer, and for you to plot it that way can be misleading until you are clear on what you're doing with that. Basic signal operations that are used freely are sequence shift or delay. So we replace n by n minus n naught. That defines a new signal. And n naught can be positive or negative. If n naught is positive, then the signal is delayed. If n naught is negative, then the signal is advanced. So it's a matter of, if n naught is positive, the signal moves to the right. If n naught is negative, the signal moves to the left. So it's earlier than what the unshifted version is. We use shift operators a lot. Special sequence, and there's a number of those. There's not a huge number, but a special sequence is the unit sample or impulse, and that's the discrete time equivalent to the delta function from continuous time signals and systems. However, this discrete time delta or unit sample sequence doesn't have any of the hang-ups that you would have with the continuous time delta. The continuous time delta is a little bit touchy, right? When I say touchy, I mean you got to just look at it just right, because it's a special function that is zero everywhere except at the location where the impulse turns on, which is when its argument is 0. And then it has 0 width and infinite height such that its area is equal to 1, remember? That's kind of a bizarre function. As a matter of fact, mathematicians aren't really fond of that idea either. It's just something that's hard to deal with, and everybody's had probability and random variables. If you want to discuss the density function of a discrete time random variable, you can also use a delta function to say there's a blob of probability at a certain point on the real line. I'm thinking of like a coin flip. A coin flip has two deltas in it. One at heads, it has a delta that has an area of 1/2, and one at tails, which has a delta of 1/2, and you can make heads and tails be 0 and 1 or something like that. So it has the same nice properties from an engineering standpoint, but the deep down mathematical part of it is just very sensitive. In the discrete time domain, though, we don't have that problem because it's just very precisely defined. It's 0 everywhere except when its argument is equal to 0, then it's going to be 1. No ambiguities there. You can write any sequence as a linear combination of time-shifted unit sample sequences or delta functions. All you have to do is just take the location of a signal sample and weight it with the value of that signal. So now we're going to use the sum index k to just grab the weights off of the signal itself and then locate it on the axes n with the time-shifted delta. This seems like a wasteful kind of a statement to just say, I can do that. But the reason why it's useful is when we go through superposition and convolution sum a little bit later today, this is a useful means to expand a signal like this, is a linear combination of time-shifted deltas. So this is just an example that appears in the book. It's just saying, I'm going to put some weights on, and I'm going to locate those weights with the time-shifted deltas along the axes n. And I could open up an example in a tool like Python or Julia right now, but I'm going to wait and do something like that a little bit later. The next sequence along the way is the unit step sequence, and this is just a, we'll see as an accumulated version of the unit impulse. So this is a sequence that turns on for n greater than or equal to 0 and is 0 for n less than 0. And it is analogous to, u of t in the continuous time domain, but u of t in the continuous time domain is typically defined to be 0 for t less than 0, 1 for t greater than 0, and then not defined for t equals 0. Remember that? That's troubling too, isn't it? Is it halfway at that point? I mean, in the continuous time domain, the unit step function is just a nice model. Reality is not there entirely. I say not there because in a real dynamical system, there has to be a finite rise and fall time. It can't jump instantaneously. Nothing can do that physically. There's always a parasitic element in an analog system, inductance, capacitance, and resistance, which will make that not be undefined. It will make it have to go through some point, but that point maybe isn't known until you describe more about the system. In the discrete time domain, though, it's very precise. It turns on precisely at n is equal to 0. So we can relate u of n and delta of n through these two different formulations. We can accumulate from k is equal to minus infinity to n to get delta of k to become u of n, and I generally like to draw a picture about that. So if I was taking this sum and I was going to describe what was happening, I would make a k-axis, and I'm going to say that, I guess I should use a different color there. That's delta of k, and then I'm going to start summing from minus infinity. I'm going to sum up to some value, sum up to some other value. So I'm considering my sum as stopping where those square brackets are. So if I sum up to less than 0, I never capture the red delta function, and my output is 0. If I stop summing at k is equal to 0, which would be equivalent to n, then I'm going to get 1, and then when I'm greater than 0, I'll always get 1 because I'm always going to be capturing the delta. Make sense? I'm just trying to make you think a little bit about how you can look at sums. And one of the things this class does a lot of is works with summations and properties of sums and manipulations of sums through changes of variables and things like that. It sounds scary. It's easier than calculus. I mean, you change variables and integrals in continuous time, so we have to do that here, and we're doing it with sums. So now I'm going to take the other point of view. There's always two ways to do something like this, I mean, in most of these types of problems. So I'm going to do this picture, and then this is the delta. So delta of n minus k, that's going to occur where? When k is equal to n, right? So I put an n right down here. And now I'm going to start summing from here, because my lower sum is 0, and then I'm moving my sum along here, and if I stop less than n, I have not captured the delta, so I get 0. If I stop summing, well, no, sum to infinity, never mind. I'm summing up to infinity always. I'm thinking of the other form. So I'm always going out to infinity. The trick is if n is less than 0, then the delta is sitting right over here. And I'm not capturing it. So I get the same net effect. As long as n is greater than or equal to 0, it gets captured, and I get an output of 1. If n is less than 0, it never gets captured, and I get 0. These are the equivalent expressions you would have from continuous time signals and systems, where you're having a delta function and you're integrating a time-shifted delta function. This is what the unit step looks like, unshifted. Of course, it can be shifted. And then another kind of relationship to see differences on, if we have, in the continuous time domain, if we have a unit step, we learn that operational calculus, and I'm going to explain that in a second, allows us to take the derivative of the step and get back to the delta. So what's the analogous thing in the discrete time domain? It's the first backwards difference is the equivalent to that. So we take u of n minus 1, so we shift the delta function to the right by one sample, subtract it from the original delta step sequence, and we get back an isolated delta at n is equal to 0. So that's first backwards difference. So what did I mean when I said operational calculus? That's my terminology, and it's because a long, long time ago I took a couple courses from the math department for my master's degree, and they were called, the book that I took the courses out of was called Operational Mathematics. And I think about that book. It was written by an applied mathematician from the University of Michigan, and we were solving boundary value problems, partial differential equations, and we were using Laplace transform techniques as much as possible. And we were doing things with steps. I don't know if we had deltas in there, but so operational mathematics is going through the motions of saying, what would the derivative of a step function be if we could relax the definition of derivatives? Because remember, a derivative is only defined if the limit from the left equals the limit from the right, for the slope at that point. Remember that from calculus? But an advanced idea would say, we can relax that and say, we don't care about the limit as much as we do just functionally, what is it doing? And the function comes along. Get this back again. So I'm putting the parenthesis on the upper and lower part saying that that's an open interval, so there's no point defined there. But we're just saying operationally it looks like it instantaneously jumps from 0 to 1. It's not defined, but we're going to just define it to be a delta. I'm too old to remember where I first saw that, but I know it wasn't in calculus. It was somewhere else. Does anybody here remember? Did you see it in Signals and Systems? I know you would have seen it there, but can you remember seeing it anywhere else? It's an operational concept, though. Differentiating a step gives a delta, just like if you differentiate a triangle waveform, you get two step functions, right? So we have this property in Signals and Systems that we can differentiate to go in one direction, and then we can integrate to go back in the other direction. And this was going in the other direction where we had an integral. And in general, these are called singularity functions because they do ultimately end up in singularities like that lead to the delta function. Let me just think. You can actually take a derivative of a delta function and get a what's that called again? A doublet is what that one's called. Remember seeing that in Signals and Systems? I'm curious, did Dr. Trimboli ever mention the doublet? Control systems people talk about it, and I think physics does too. A doublet would be, it's bizarre because if you differentiate this, I'm going off-roading right now a little bit, but if this was the model for the delta, right, minus epsilon over 2 to plus epsilon over 2, and then the height here, is 1 over epsilon. So the area of that rectangle is 1 over epsilon times epsilon, so it's 1. So it satisfies it's called a test function for a delta function. So we can differentiate this, right, using this operational math idea. And what's going to happen is there's going to be a delta right there where it steps up because there's a change, and then there'll be a delta right there where it steps down. And as epsilon goes to 0, those two deltas, the one pointing up and the one pointing down, both stand on top of each other. That's why it's called a doublet. And the best way I can think of it is it'd be like in mechanics or something. I'm going to try not to sound too crude, but it'd be like getting hit by a sledgehammer, first getting bounced up really hard and then getting bounced down really hard, because that's what a delta function also can be used to represent the transfer of momentum on an impact. I'm thinking of a pool table. When the cue ball hits the ball, momentum transfers immediately, and that's like a delta function. But in a car accident or some bad thing, you might get hit twice, once up and then once down. Interesting. I never planned to talk about it today, but I just decided I should get into it a little bit. Interesting concepts, though. Everything that electrical engineers do and physicists do mostly too is we want to use the math as a tool to get our work done, and we kind of make the rules work in such a way that maybe it stresses the pure mathematics really hard, but we're always taking the approach of physics behind us, that it's something that's realizable. So the true delta function doesn't exist, but a very short pulse does exist in a real scenario, such that if you stand way back from that rectangular pulse, way back, it looks like a delta, right? That's the idea. Or if you zoom into it. So the idea of the doublet would be that same idea. The whacking up, whacking down would not occur instantaneously. They would just be like microseconds or picoseconds apart, but it's still a math model for it. Okay, the next waveform I want to go through is the exponential sequence. And this one has intriguing possibilities that will linger on for a while, and we'll get back to more when we talk about the discrete time Fourier transform, or DFT, which then leads to the FFT. So the exponential sequence has got this form. A is the amplitude, alpha as a constant, and n as the time index. Both A and alpha can be complex in general, but one example would be both real, and we're going to get an exponential decay as n goes off to infinity. But for n negative, then it's going to be exponentially growing if alpha is bounded between 0 and 1. But frequently, though, the way we see this, most of the time we're going to see something like A alpha to the n, u of n. My pen messed up there a little bit. It's not tracking. It stopped working there. How do these pens work, by the way? They use Bluetooth. Is Bluetooth fallible? And there's a little button on the top. I just pressed it again to get it to reconnect, so it stopped for a moment. So this is a decaying exponential, and that's a pretty popular, common type of excitation signal. If I didn't put the u of n on there, then the exponential would be growing on the negative side and decaying on the positive side. And if alpha is negative, but still less than 1, then it would be an alternating sequence. Second case of interest, though, is having a complex value for alpha. So alpha has some magnitude of alpha, and then it has an angle e to the j omega naught. So this is going to create a complex sinusoid, which is right down here. And if we want to turn off the alpha and just set it equal to 1, then we're going to have a true complex sinusoid that's constant envelope. Otherwise, it's decaying or growing exponentially. And then we can use Euler's identity to write that in terms of a cosine and a sine. Or we can just take a variation of this and just take the real part or the imaginary part, and we can throw the u of n on there. So this leads to a bunch of variations, but it's all rooted abstractly in the idea of the exponential sequence. The book introduces it this way, so I'm not changing that, but I think in retrospect, from all the years that I've been teaching out of this book, this is kind of building too much up into side of one simple thing to say we have a alpha to the n and then say, oh, by the way, it could be real complex and so on, just makes it pack too much stuff inside of one thing. I would rather just think of the real exponential, usually with a u of n or u of minus n, so it doesn't go in both directions. And then complex sinusoid or real sinusoid. I mean, a signal that is not included here, but one that we will see. We are going to see alpha to the absolute value of n. So it'll be some sequence that decays off like that. We're going to bump into that pretty quickly. That's just a two-sided decaying exponential. But here's the real exponential without the u of n, so it's growing unbounded as you go to the left. It's decaying as you go to the right. And then the special case of the complex sinusoid, just viewing it now as the real part, it would be the familiar real cosine sequence, a cosine omega naught n plus phi. And the notation that we would use for these units would be in the modeling, we're going to think of omega naught as being radians, but it's actually radians per sample, because if we're multiplying, the argument of a trig function is radians, right? And n is samples, so it's, but n is not really, doesn't really have a dimension, so, but it's convenient to think of it as radians per sample. I'm not trying to get you all confused, but one of the fundamental things that I go back to when I was a freshman taking chemistry a long, long time ago, and I never took chemistry in high school, so I was at a disadvantage. Why didn't I take it? Because I took electronics. I took a lot of electronics courses at the high school I went to, and was going to maybe be a radio and TV repairman, because I got advanced placement at the tech school in my community. So when I started in chemistry, I remember them talking about balancing your units and all the calculations we were doing and so on. So that idea has stuck with me and extended itself out to something that I think all engineers know, that you check that your units work out properly. And a lot of times you find a flaw in your analysis if you haven't, due to a units error. You want to see if the units come out properly. So I'm interested in that. But radians is kind of a quirky thing in my mind. We like to use degrees a lot, but degrees don't work in a trig function. You have to convert it to radians. And then in this instance, omega naught is really got units of radians, but it's nice to think of n as having a unit of sample, and then we can say radians per sample, but it's still kind of artificial to say that. Okay, one of the interesting properties, though, and this is the brain teaser part of this little episode, is complex sinusoids that are also, or real sinusoids that are also periodic. And so we're going to use this, we're going to be just exploring this definition a little bit. And those of you that are taking the lab, I think it's the second problem of the lab exercises has you looking at periodicities of sequences, right? And by the way, there's a Jupyter notebook up there that's for either Julia or Python that I put on the website. It's actually, yeah, I think it's on the website. And it's got all the blanks in there so you can just code and put your answers right, bing, 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 right in the notebook, whichever language you choose to do it in. But the definition of a periodic sequence is that you can take a sequence x of n and you can just pick it up and move it over by some integer n and it will look identical. So the sequence runs from minus to plus infinity, but it's got a period n, and that's the smallest integer that you can do that with. And if we look at the formula for a cosine, it's periodic, or it's indistinguishable if you take omega naught and shift it by a multiple of 2 pi. So now what we're going to do is we're going to take that idea, something that you've lived with all your engineering life, I'll just speculate, that a cosine sequence is always periodic. I mean, a cosine wave is always periodic because trig functions have this modulo 2 pi property. But now, if you marry these two things together, we're going to find that it doesn't guarantee that the sequence is periodic. And this is going to be a little bit earth-shattering, I think, to your common sense, right? Because you go up to the lab, turn on a function generator, look at it on the scope, say it's periodic, it repeats, the sync of the scope locks onto it. If you do the Fourier transform of it, you see that it has a single spike at the frequency plus the negative frequency, however you're displaying it, or take its Fourier transform. But let's just drill into this a little bit. So this example is periodicity of the sinusoidal sequence. So we have a cosine omega naught n plus phi, and then if we want to establish conditions that ensure that it's a periodic sequence, we're going to replace n by n plus n naught, or n plus capital N. So you can see I've just expanded it out because I'm saying n is going to go to n plus capital N. And if those two are equal, then we've established that the sequence is periodic. So we go inside the argument and we see that in order to have this true, I'm just going to erase this now. That right there has to be irrelevant. In other words, it has to be a multiple of 2 pi, right? Because that we know hard and fast is part of cosine and sine and so on. So we'll say omega naught n is equal to 2 pi times k. And then just rearranging that, we'll say that omega naught then is constrained not to be any number we choose, which in the case of a continuous time cosine or sine wave makes it periodic under all circumstances. We'll see in the case of a discrete time sine or cosine sequence, omega naught has to be chosen such that it's 2 pi times a ratio of two integers, k over n, where the denominator is going to be the period. And LCM, least common multiple, it can be a useful tool if you're using it in Python or MATLAB, or I guess Julia has LCM. I haven't really looked into it, wanting to do that. But so this tells us what it guarantees it to be periodic. And if we have two sequences that we want to sum together that are sinusoids and periodic, then we need to get them to be commensurate, which means the period of one has to be equal to the other or fit within multiple periods of the second sinusoid. That's the idea of commensurate. But for a single sinusoid, we just have to be able to have omega naught be this ratio k over n, where k is any integer, and it turns out to be on the fundamental interval, we have to have k run something like that. Actually, it's going to be that. We can have k equals 0, in which case it's just a constant. Cosine of 0 would be 1. But for the fundamental interval, we just have to have k lie somewhere between 0 and actually less than or equal to n minus 1. So I took an example here. Suppose omega naught is 5 pi over n. Is this acceptable to be a periodic sequence? So we have to find the smallest n that satisfies this equation. So the way I do that is I would write it out and then going up to the definition there, I would pull out 2 pi. So if I pull out 2 pi, I'm going to have to put a 2 in the numerator. Well, I'm going to pull out 2 pi, and then I'm going to have 5 over what? What do I have to do? I might have to put 16 in there, right? So it stays balanced. So that says it's going to be 16. Is this following? Is this disturbing? I'm just curious. Okay, you're good with it. Is this something you did in 3205? Because I don't know. I mean, what is engineering about? It's about problem solving, right? Customer has a problem, you have to go solve it. Along the way of solving the customer's problems, frequently you'll bump into little things like this, like, oh, I never realized that, or oh, that's going to be a factor in how my solution gets developed. And these things just are always happening, just like something mundane like taking out the garbage. I never noticed that there was a mouse in the bottom of the garbage can, or something, you know, that you didn't really want to see, but you look in your garbage can and there it is. You smelled it maybe before you saw it, but why did I think of that as an example? Because when I was in graduate school, I lived in a trailer park in Missouri, in the hills near Rolla, Missouri, and it was called a mobile home by my landlord. I wouldn't call it mobile, but you can tell that he probably had a little bit of an accent, a southern accent. One day I was having problems. I was hearing some sounds in my garbage can right in my kitchen area, and some mice had gotten in there and they couldn't get out. And it was kind of a shock to me, but considering that there were holes in the floor of the trailer, it didn't surprise me that they were there. Maybe they weren't alive, I don't remember anymore. I just remember that they were there. Okay, so indistinguishable frequencies are going to be what happens when we go outside this interval 0 up to n minus 1. Those will be the periodic extensions of the so-called fundamental frequency. So if we think about n as being the basis or the period, we can have n distinguishable frequencies. We can have DC 1 over n, 2 over n, all the way up to n minus 1 over n. And these end up being the distinguishable frequencies. And when we go into the discrete time Fourier transform, dTFT, which leads to the FFT, all of those points that are used in the DFT, and hence the FFT, are the corresponding, sometimes called the bin frequencies, or the distinguishable frequencies of the FFT. And if we go at multiples of that, harmonics above that distinguishable range, they just land back on the same frequencies again when we modularize them back to this interval 0 to n minus 1. So there's that relationship, and then there's also the relationship in sampling theory that you have aliases, and if you're sampling at 1 kilohertz and you go above the folding frequency, you find out if you're, say, at 4 kilohertz and you go above up to 6 kilohertz, 4 kilohertz and 6 kilohertz end up being indistinguishable. So it's the same, it's a similar idea. It's not quite identical. That's a little bit of a added twist on top of that. But if you were to go to 400 and then go to 1100, that would be 100 hertz above the sampling frequency. That would be going up to the next band of frequencies. 0 to n minus 1 would correspond to 0 to the sampling frequency minus 1 over n. The fact that you can fold at half the frequency has to do with, see if I can write this down, because this shows up in an example that's, I think, it's coming up pretty soon. So that's 8 pi over 10. So I'll take that 8, 12 pi over 10. Those are equivalent because we're also taking it using the fact that cosine's an even function. Let's just see, do I have an example like that in here? I guess I don't. I have some pictures, but let's just dissect that down since I wrote it up on the paper. What's going on here? If I take 12 pi over n, I can break that into 10 plus 2. And I guess I did this, maybe I did this the wrong way. Okay, I did this okay though. That's going to be, let's see, that's going to be 2 pi over 10. I didn't want to go in that direction, which would be 1/5. I think I wanted to take this in a different direction. What I wanted to establish is this. I'll just write out what I'm going after before I get there. Lost one of my colors. I'm trying to figure out where did that color go to. I don't have green anymore. I must have accidentally gotten rid of it. Oh, there it is, right there. I'm just trying to establish is that those two frequencies are equivalent, and maybe this example wasn't drawing the picture properly, so that's going to be n over 2. So 1, 2, 3, 4. I'm going to cheat. I'm going to change my problem because this was off the top of my head and I wasn't thinking properly about how to set up a good example. So I'm going to in particular say n is equal to 8. So I'm going to do that case right there. I'm looking at values of k relative to n. This is not a spectrum plot per se, it's just looking at k relative to n for n is equal to 8. So I'm going to plug in this case I'm going to say, suppose I have a sinusoidal frequency at 2 pi times 5 over 8 n. And then what I want to do is see that that's going to be equivalent to 2 pi times 3 over 8 times n. So I'm going to take the frequency 2 pi 5 over 8, which is omega naught, and I'm going to subtract 2 pi from it. So when I do that, I'm going to have 5 minus 8, which is minus 3, right? If I'm just over 8. But then if I carry this forward, I'd be talking about cosine of 2 pi having a minus sign in there, but then because cosine is even, cosine 2 pi 3 over 8 times n. So I'm just saying, for the case of a real sinusoid, 3 and 5 are equivalent frequencies, and that also relates back to the idea of the folding frequency from sampling theory. If it's a complex sinusoid, then 3 and 5 are not equal, but for a real sinusoid, they are equal. And now, in order to explain this, I probably should go to an example in a tool. So I'm going to jump over to running something, and I may have to go grab something. Has anybody grabbed any of the examples off the website? I might just pull one of those up there. Just pull one down and install it somewhere. So I've got things for set number 1 for help, and I can pull up one of those notebooks. So what I'll do is I'll just download that, and then I'll go over here to my downloads, and I will open that up. Let's see. Do an extract all, and you'll always know if I did it on a Windows machine or my MacBook, because you'll see that little extra folder in there all the time saying that I zipped it up on my Macintosh. Ignore it, it doesn't mean anything. But I'm going to take both of these, copy them, and I'm going to put them in another location. Under Documents, normally I would put them right in this folder, in my Notebooks folder, which is got a mumble jumble of all kinds of stuff, and I don't really want to mess with that right now. When I was doing my recording of the install last night, I created a new folder though. I created a folder under Projects. Let's see if I can figure out where I put that. Projects, and I called it Julia. No, I didn't call it Julia. Well, I can find out. If you hover over that, I can see where I put it. Julia Python under Documents. Notice I'm just hovering over this tab that's in the Jupyter Notebook right now, and you can see the path. So it's under Julia Python. under Documents. But why am I not seeing it here? Oh, there it is. Okay, so I'm just going to drop it in there. And now I can go over here in my Jupyter Notebook, which I launched up, and let me just, since I'm doing this, let me just kill this. I'm going to do that. And I'm going to go over here, and I'm going to do a Control-C. And this should halt it, but if it's not going to halt it, I'll force it shut. Right now it's not stopping it.
Control-C.
That's not working. I'm going to do, nope. I'm not against killing the whole thing, but it should just be Control-C to stop it. The problem is whenever I'm running my screencasting software, there's shortcut keys that are overridden by that software, so I don't know whether there's an interaction going on. I'm just going to kill it. I happen to have another console that I opened up. But let me just explain a little bit about what happened after I did my install. When I did my install last night, I really didn't take any time to go see what I was getting, but if I was to go down here under Julia, it's going to open up a terminal for me directly. But what I will frequently do, and Control-D is what you can do to kill it, what I'll frequently do is either open up a PowerShell, and I can do a PowerShell here, which is the one that comes with your operating system, and I should be able to launch it from here. All well and fine, but and then I can type exit to leave that. But what I've done is I've gone to the Microsoft Store, and I've, down here, and I've actually installed Terminal, and then I get a multi-tabbed terminal that I can do a lot of different things with. So I'm just searching on the store for Terminal, and Windows Terminal is what I'm running. And you can see that I've downloaded it. It's free. It doesn't cost anything. But that's what I'm using, so I can just be in one terminal. I can open up multiple copies, or if I want to run my Windows subsystem for Linux, I can open up that too. So I just have that as kind of a fallback. You don't have to go that way if you don't want to. You can just launch the icon like you're used to, and then you'll be able to do it that way. So maybe I should just play by the simpler rules right now. I'm just saying, and then what I would do is I would go put that up into my start menu here. So I would go under here to Julia 1.8, pin to start. For me, make it small, and move it right there, and then I can start it from there. So I'd be going to here. I could click my right bracket, and then I'd see my package manager. Just do a quick status check to see that all the packages got installed. If at some point you feel like packages are out of date, you can just type up and enter, and that will upgrade your packages. It will not upgrade things for Python though, and Jupyter. You'll have to load up Conda to do that. So I'm going to hit the backspace key, and I'll be back to the Julia prompt. Because I've also installed, I'm just hitting the up arrow key. What I should do though is I could go using this my REPL, and it needs to be a capital O. All packages start with a capital. And then I'll get colorized syntax in this terminal, but I don't spend much time here, but I explain in the document how you can have a startup folder, and you can have things start up automatically, like you could put it to start iJulia automatically. I wouldn't have it launch it. You might just do an import, so I'm going to do an import iJulia. You can see now I'm getting colorizations. And then at this point, I've got the package installed, so now I just have to import it. I have to run its first name and put a dot, and then I'm going to run Jupyter Lab. And I don't remember whether it's capital or not. I think isn't it this? Isn't that it or not? If not, I have to go look again. But looking at the cheat sheet multiple times is good. It's there for a reason. It's there to help jog your mind. So it is Jupyter Lab that I'm going to run. So I've just done those two commands. So go to here. And yeah, I didn't put a J in Julia. I didn't put a J in there, right there. Okay. I mean, a capital J is what I meant to say. All this stuff blows on your screen immediately. Don't worry about it. It's just there, and now it's launching it. It's bringing up Jupyter Lab. And then it's remembering what I had up last time. If I need to remember what I can have a new launcher to tell me what things I can do, I might take this launcher and move it over to here. Now I've got that capability. You've got a more complicated interface you can go to. You can use a debugger if you want to and other things. I'm not expecting you to fumble with that if you want, but you can whenever you feel like it. But now what I'm going to do is I'm going to go to this first tab and just search. So I'm in this folder, and these are the things I just put in. I have, if I slide this over, I can see what it is I put in. I have the Python demo version or the Julia demo version. Does anybody have a preference which one you want to see me run? I'll run one or the other for this little quick demo I was going to do right now. Flip a coin. I guess I'm just curious right now about all of you. I know many of you used Python before, but is there anybody that hasn't used Python before? Just so I know that you're sort of neutral. You're going to be like this. I can go here. I can go there. Okay, you've never used each, but you used MATLAB, right? So I'm going to be curious. I'm doing a psychological study in a sense. I'm going to be curious for those, if you've never used Python, but you've used MATLAB, you're going to see some things in Julia that are very much like exactly as in MATLAB. And when you go to Python, you have to give that up for something new. And it's kind of they're all three similar but not the same. So you might, if you immediately jump to Julia, you might say, hey, this is easier because it's got these MATLAB features, and you won't learn things about Python that you'll have to flip back over to. But I'm not you. I just know in retrospect, if I would have never learned Python, I probably would have a different thought process. So your brain is moldable right now the way I see it. Does that make sense? In a strange way. Unfortunately, though, in the work environment, Julia is so new for a lot of companies that you're either going to be using Python or MATLAB, probably. But no choices right now. No cares. I mean, Python is definitely easier for me, 100%, and maybe I'll just pick that one. I'm just trying to give you equal choices. So I double-click that. It's opened up. This little guy here displays the table of contents, so you can right away just click on things over here and see the headers that I've put in from Markdown. And this is for LaTeX rendering. You can delete that cell with a garbage can here if you want to. This is a new feature that allows you to navigate around in the notebook. You can just click here if you want to, but you can add a cell above or below. You can copy cells, but you can use these guys to copy cells. This is a feature that came about early summer 2022. So some of you that were in CommLab, you didn't see this because this version just came out in May, I think, late May. At any rate, I have a bunch of things that I run here: import NumPy, import graphics, import SigSys from my signals and systems package, and then I'm importing scipy.signal. And then a couple of other things. I like to use scalable vector graphics because they're a lot sharper than the PNG graphics. This cell I moved down, I'm going to move it back up by just grabbing it. That puts a new page in, but it doesn't matter for here. So here's some markdown, and I've just encoded in some typeset syntax from LaTeX, something you might pick up on by just looking at examples like this. If I double-click or Shift-Enter on any cell, it compiles it or formats it. So in this case, it's just nice-looking text. But in terms of things we were looking at earlier, this is just kicking things off, saying I want to have a range of integers running from -5 up to 10 -1, because everything in Python starts at index 0 and starts one number less. Julia, both languages use # as a comment character, but in Julia you would use collect, and you're going to use something like 0 colon to 10, and that will stop at 10. And this is just like in MATLAB, right? If you wanted to create an array that goes from 0 up to and inclusive of 10, you would do that. In Python, I have to do that because it's going to stop at 1 less. I'm just throwing that out there for kind of the fun of it. But now I'm going to take advantage of functions that I have in my library, and if I space away from the SS, and the SS is an alias for the full name of SigSys, so I've just imported it and given it an alias. Does everybody know what an alias is? Do any of you have an alias? Maybe, right? Your parents probably gave you an alias. My parents surely did. It's not fun to repeat it, but parents have a way of giving all their children aliases, you know, the short name that your family uses. At any rate, so SS, if I just type the dot there and hit tab, hit the tab key, it immediately tells me all the functions that are in this library of SigSys. And I've created primitives in here for doing a lot of different things like convolution sum, principal alias, PN generator, random bit or NRZ bit streams, a lot of different things. Things we're going to look at would be like discrete step and d-impulse. So I chose d-impulse here, and then if I do a shift tab whenever I'm in the argument of a function, I will get the docstring or the help file available for that function. So you can see it. There might be some examples. And all of this comes from, if we're using scikit DSP.com, it all comes from the package and the read the docs site, which was created for the package when I created it with my co-author, Charanth, who is the lab instructor that you guys have. He's the brains behind the computer engineering side. I'm more the brains behind the algorithms and the code that went into this. But we're into this module right now, SigSys. So if we type SigSys, then this is the listing of all the functions and examples and things that SigSys has in it. But the short version of the docstring version does pop up, and we were looking at d delta, and I don't know where it is in this long list of functions. I think there's a way of listing that from read the docs, but okay, here it is. D impulse. So if I want to see the source code of what I wrote a few years back, there's what the function looks like. The function is just a little bit of code. It's just all of that is all there is to it. The rest of it's just docstring help. And all of that docstring help between the triple quotes there is what this is right here. To me, that's nice because I don't have to remember all this stuff. I have it documented in there, and it's on the internet, but it's available right on the fly right here. So impulse, and I'm going to shift it by 2, and then I'm going to do a stem plot. This was needed in an earlier version. I just didn't delete it, but there it is. There's my delta, and if I wanted to be a little bit more complete, I would say X label, and generally you put an R in front of it and a single tick mark. R means interpreted as raw, so I can say index, and then I can put LaTeX in here to get a properly italics math version, and then I can say Y label. If I start typing it and hit tab, it will try to finish it for me too, because it's has a search string capability. So R, and usually for here I'll put something like amplitude. Again, a single tick. And now it's there. I already turned the grid on, and I could, I guess if I want to be complete here, I need to put a title in. Single delta is all I wanted to make out of that. So now I've got the complete graphics there. And if you export the notebook as HTML and various other things, you can get it for parts of homework hand-ins. If you don't want to do that, you can also just, oops, wrong button. Trying to remember, I can do a screenshot of this and put it in a Word document and print it out.
What is the R for the quotes?
Okay, good question. It means interpret this string as raw, which means the symbols and things will be interpreted literally rather than doing some conversion on them. Does that make sense?
Yeah.
I'm not an expert. I just know that if I don't do it, like if I don't do it here, notice that's an italic N. If I don't do it here, it's still working, but some symbols don't come out correct. Like maybe if I had to put A sub N, that came out okay too. I've just been in the habit for a long time. Maybe you don't need to do it anymore. These open source languages are constantly being worked on by the community, and sometimes things aren't needed, but raw, R means raw, and then there's other precursors. If you don't need it, don't put it down, but like I said, I'm in the habit of just always including it. So there that is, and if I wanted to shift this, I could quickly define another symbol, N0, to be equal to 3, and then I could just replace that by N0, and now the delta is sitting over there at 3, or if I wanted it to be minus 5, now it's sitting over there at minus 5. So I can just do operations, and the beauty of Python is that N0 is a scalar, but N is an array. So if I just quickly add a cell up above here and look at what N turned into, N was defined with the arange command, so it ended up being an array that contains those values. But if I do a scalar operation with that array, it just does a pointwise operation automatically. In Julia, because it has that property a little bit more like MATLAB, in Julia you'd have to do N dot minus N0, because it would grump at you saying there's a vector in one argument, and one of the variables is an array and the other one's a scalar. And remember MATLAB? All of you learned MATLAB, you had to use dots liberally at times, right? When you first learned the language, I remember, it's like, do I need a dot or do I don't need a dot? And then the computer would always ding at you if you didn't get it. So does anybody ever remember that, getting all these dings? We're going to take a break here pretty quick too. So We'll take a break actually now, and then I'll come back and finish playing around here a little bit. Put that back at 3. Other examples in here, which I want to look at later in class, are related to the homework problems. This is a homework problem you have, but what I can do is I'm going to carry on after break and put a new cell in here and talk about the sinusoid signal periodicity, which is kind of where I stopped lecturing on a while ago. Okay, we're back from break. I was going through some examples, and I'll lead up to this. I was asked the question during the break about how do you want the homework turned in, and what I want for the homework is, because I want it electronic so I can return it electronic, I want it on Slack. It works really well. It has worked well in the past. You're going to have these fingers represent your handwritten pages for your solution. These fingers might represent pages that you've done a problem on Julia or Python in Jupyter Notebook, and you're going to have a page that has some code and then has some plots. So how are you going to get these two things to come together? There's PDF combining tools out there, and Ryan, am I right? Is that your name's Ryan, right? Or Caleb. Close. Sorry about that. There's different tools out there, and Adobe has got something, but I just did a quick search over merge PDF files. So what you'll do for your handwritten copies, you might use a scanner you've got on your phone or one in the library, and then these will be produced right on the computer, and then you just need to put the computer solutions right after part A or at the end of the problem, so that way when I'm grading the handwritten part, I'll look for the computer part, the code, and the graphic. Do not give me just graphics, because I won't know what the code is, and if the graphic's wrong, tell me the story, so I need the code cell. So one approach to getting that from the notebook is to just take a section in here like what we just did, and in order to do that, sometimes I have to shrink this down, so I might have to make this smaller, making it bigger now. But I might do it in a couple of screenshots. So I might do some things here where I'm going to take a screenshot of that. That's not a very good alignment, and then paste that in a Word document, and then export that as PDF, break it apart, and do all these things. And that works well. That's the way I've done a lot of my solutions originally. I use FrameMaker, but I get the idea there of how that's done. But I was just mentioning that what you can do on the notebook, and it should work, but it wasn't working just now. If you've got a notebook document like this, you can go up to File and Export. There's a lot of different export formats, but you have to have different tools installed to do that, and some of them don't work. HTML has worked in the past, but it didn't take the graphic on this notebook for whatever reason. PDF requires LaTeX. Some of these other things you can try out. They keep adding more things, but you sometimes have to have more tools installed. But Markdown has been a mainstay for me. It exports out a Markdown file of everything, and then it exports out the graphics, and that's what I was looking at over here. I had exported out that document as a zip, and then it became this folder. All the graphics were saved as scalable vector graphics, and then there's a Markdown file. And what can import this folder immediately is Typora. It will import it. It used to be free, and then last spring it became a for-charge app. It runs on Windows, Mac, and Linux. I use it for doing a lot of my writing. I did it for creating this document over here. It's very fast, very efficient. It's an amazing tool, actually, I think, for writing documents. But you'll have to buy one of these. And I bought one, a licensed seat of it, for $14.99, and then you get 3 uses of the license code, and I have it installed on 3 machines right now, so I have to give it up if I want to put it on here again. But that works really well, and then I have a file that allows you to put in a cell of dash dash dash, and that puts in a horizontal bar, but it also paginates. It forces a page break right there. There's different ways of doing page breaks, so that way you could have different, ensuring that you could be able to separate out your solutions into separate problem 1, problem 5, and so on, that sort of thing. I'll maybe talk a little bit more about that on another occasion, but the screenshotting works good also. So that's out there. I mentioned Typora in the syllabus, so you've got that to go look at if you wanted to. So does that answer enough of that question?
Thank you.
Yeah, I answered it. I whammed it into the ground, not with a doublet, with just a single sledgehammer, right? It hit bedrock. I tend to be a no-nonsense guy. If I'm hiring a contractor to do something around my house, it's like, this is what I want you to do. It's like, do this and I will be happy. They show me the work, and if they haven't done what I asked them to do, I say, you didn't do what I asked you to do. You got to do this. Maybe it's my engineering instinct to say I want it done, and this is exactly what I want. No negotiating. Okay, so I brought up the Julia notebook while you were on break, and it looks almost identical. There's a few other pieces because there's a library of code that handles some things. It's over here in this folder called, oops, I did that same thing again. It's in this modules thing. At any rate, when you go ahead and do things like we were just doing, the delta, I have collect in here, and help in Julia is the same way, shift tab, and that should bring me help. There it is. It took a while for it to come up, but that's the help on collect. And then my stem function plot, it just gives me the doc string, a very simple doc string I wrote for my stem function helper, or in DSP tools it just says put in N and X, and then you can optionally define a title with these things. You have to put in the semicolon, but this example in the Julia language has got some interesting things in it too that we don't have in Python, and that is if you want to type with symbols to be like beta, I can have a variable named beta. So I can have things look more like syntax of math if I want to. You have to type a backslash and then hit a tab key, and then it will convert it like that. I'm not going to dwell on the Julia side anymore right now. I'm going to go right on to what we were looking at, though. If we jump back over to the notes, I have an example in some notebook somewhere on the system, but I'm just going to sort of start from scratch. So I'm going to just do, in Python here, I'm going to create a new cell, and I'm just going to say I started to type collect because I've been typing too much Julia lately. I'm going to do a range, and I'm going to go -10 to 10, and then I'm going to create x1 to be equal to the cosine of 2 times pi times 3 over 5 times n. And then I'm going to go up and copy that line. And this computer doesn't have the same keys on it that my other one does. So what we were doing, we did 5, 3. That's not what we did, though. What did we do in the example? I want to go back and repeat that. I started with cosine 2 pi 5 over 8 times n, and then I wanted to show ultimately I came along and said 2 pi 3 over 8 is the same as 2 pi 5 over 8, because I was trying to say those were the same, right? Remember me doing that? I was doing the math of that, so I'm gonna create that exact problem. So I guess I better put the 8 in there instead. So I'll just run that. I did not attach the plot to it, so now what I need to do, and I'm going to do this in a particular way, I'm going to use subplot, so I have two separate plots, one stacked on top of the other. In Julia, this is a little bit more complicated, but this is very similar to the way it works in MATLAB. So I'm going to create a stem function plot of n, comma x1, and then I'm going to create a stem function plot of n, comma x2, and I didn't type x2 up above here. This tablet has got really small arrow keys, and my fingers don't get along with it, so I'm always hitting about 3 keys at once when I'm trying to use the arrow keys. So I sent the cursor up to the top of the screen. I didn't want to do that. So even though this doesn't look like a cosine sequence, because the period is, it's not very long. The period is only 8. I can at least look at these, and if I put a grid on here, maybe it would be better. So I could put a grid and put a grid. And I'm saying they look identical. The best way would be just to subtract them, but what I want to do is kind of, now I'm going to do sine. And sine is an odd function, so although the two sinusoids were equal if they were cosine, and if I was using 3 for k and 5 for k, if I use 3 and 5 with sine, what do I expect? Sine is an odd function, right? So one of them is going to be flipped relative to the other, because sine of minus 3 and sine of 3, which is what we reduced it down modulo 2 pi, would be opposite in sign. So let's just run this. And see, up, down, down, up, so on across the screen there. Now, I know this doesn't look very exciting. How could I make this look more exciting? Well, I could have come along here and I could have said, rather than 8, I could have gone n is equal to, I'll just say 120, if I can get my keys to work on here. Well, 100. Well, let's not go that big. I'm going from minus 10 to plus 10. So I'm going to make a couple changes here. This is how I learn things on the computer. So you're watching me in action. I model something and I'm trying to get a physical understanding of it. So I go to the computer and start messing around with some of the variables to try to get a picture that suits my intuition and makes my brain feel good about things. I mean, when I say feel good about things, I'm seeing the concept come to life. So I'm going to take this up a little bit bigger. I guess I'll go to 50. So I'm going to put n down in there, n down in there, and I'm going to keep the frequencies slow or low. So what I'm going to have to do is I'm going to have to say, if n is 50, and I go back to my picture over here, so if I want to see this periodicity property, I'm going to count up 3 from 0, and then I'm going to count down 3 from 50. So I'm going to go, and so what index would I put in there? I would go 49, 48, 47. Is that right? Does everybody see what I'm doing? I'm just trying to show that these will be equivalent. So I'm going to write that into my code then. So I'm going to go 3 and 47. And I'm going to go back to cosine. Go back to cosine. And I've now got to make this, I'll make this be minus 50, oops, to 50. So I'm going to span 2 periods. Now the waveform looks more pleasant to your eye, right? It looks sinusoidal-like rather than what we were seeing as only a few samples over one period. But I'm seeing that as, I mean, I could take the subtraction, but my eyeballs are telling me it looks pretty good. I mean, and those of you in the lab, this is what you're going to be doing in that second problem in the lab, where you're playing around with finding periodicities of the sum of sinusoids too. But now if I change this to sine, and by the way, if I wanted to be cute here, I could use that third argument and I'd have red. So if I want to do sine and sine, and I didn't change the color of the dots, that's another option, I forgot about that. At any rate, as advertised, it's doing what I thought it would do. And the reason why I have the animation stuff for both Julia and Python is that you could put sliders on here. You can actually put things and move things around if you wanted to. Remember, I was going to show you that from last week for the not filter. I showed you a little bit of it, but I'm not sure I want to start up a Pluto notebook right now. But advertising says satisfaction guaranteed, right? So in engineering, satisfaction, if you can, you know, develop a little bit of code, a model to satisfy your desire to understand something. That's me. I don't know if that's you, but I want it to be you for engineering problem solving. You'd like to satisfy your understanding so that way when you go in front of your boss and say, I got this thing working, good, we're going to meet together and you're going to hand this off to this other engineer. When you hand this off to the other engineer on your team, do you want it to be working good, or do you want it to just be sort of half-baked and still broken? I contend you want it to be, you know, not broken anymore, and they're going to pick it up because they don't know DSP. They're going to implement it, and then they're going to show it to the boss, and when it doesn't work right anymore, you're going to be hauled back in to say, this doesn't seem to work. You didn't do something right, or you missed a special case and it blows up in some scenario. So pretty cool. I'll get back to talking about these things, and maybe I need to make this bigger, go in the right direction so that I can see it. No one said anything to me though. Are you seeing this stuff from the back? For some reason or other, I can't resize that right now. What's going on? My browser won't let me resize that bar on the side. But I can always get rid of it. There we go. All these buttons down here do different things. You can see kernels running and open tabs, but if you click it a second time, it just takes it away. So that's the Julia version. Here's the one we've been playing with though. So we're going to come back to this in a bit. And these are some examples that I just did of different frequencies and showing the type of thing I was just trying to show just now. This is very similar to what I just did. Pi over 4 and 7 pi over 4 are equivalent. So if you want to take a look at these examples, likewise pi over 8 and 15 pi over 8, you could go through the math that I was doing right up here in the green just to convince yourself, and then you could go to what I just did in, you know, Python to just convince yourself that that's working as expected. So now we're going to move to the next big exciting focus for DSP. And I'm saying it facetiously because unless you're into this stuff, it is dry and dull and boring. If you're a landscaper, let's say, doing landscaping for somebody, does this have anything to do with your work as a landscaper? I'd say certainly not. But, you know, landscaping can be fun for landscapers, and signal processing is fun for DSP people. So we have our gig, and we really get into it. So discrete time system, it's an operator that maps an input sequence to an output sequence. And the notation of the book, they use T, and mathematicians might use T to just say, it's a letter I picked, to say it's going to operate on the sequence to produce an output sequence. We might use L a little bit later on if we know it's a linear system, or H of H as a generalized operator, but T is good. It's what the book likes to use a lot, I think. So we're going to take as a simple example the moving average operator. And moving average is a really common statistical signal processing function. It's popular across multiple disciplines, absolutely. Eventually, when you start earning a lot of money, you're going to invest your money, and you're going to go to some investment advisor, and that he or she person is going to talk you into buying some stock, and they're going to show you how the stock performs over time, and they're going to show you this moving average and trend lines and things about investments and things like that. So business people use moving average, and statistics are used a lot. So a moving average filter is exactly what the name says. It's forming the average of past, present, and future values of the input. So you look at what you see in the equation here, and you can see, yep, I'm going to grab the input, and I'm going to take values of k for k greater than 0, which are going to be past values further down in time, and then I'm going to take future values when k is negative. So I'm going to actually do something that we can only talk about doing, because we cannot in practice take future values. But that's the thing about DSP you have to get a handle on. You can still have stored data, and you can treat moving or averaging past and future values. Does that make sense? It's part of one of the cool things about DSP is that you can have a collection of data, and the actual operator is going to could be this non-causal, as it might be called, moving average. To make it causal, though, we have to set M1 equal to 0, so we can never take negative values of the input or future values of the input. But here's a depiction of what the causal moving average is doing. It's taking the present value there, the dark N, or the dark stem, and then it's going back in time to take 5 samples into the past. So in this case, M2 is equal to 5, so it's going to have a total of 6 samples used to form the average. And then as N moves along, that window just keeps sliding along, and it keeps taking the moving average. This becomes what's called, we are now getting into part of the homework problems where you're going to be characterizing systems. So this is a good place to bring up one of the definitions of a system, and that is a property of a system, memoryless or not memoryless. So, or I mean memoryless or memory. So this moving average system is definitely memory, right? Because the present output is going to involve the average of 5 past values in the present. So it's going to involve memory. Memoryless would say it can only use the present input to form the present output. And if you go to that extreme in your system constraints, about all you can settle on is some sort of, say, a power series nonlinearity, which you could think of as being a cosine, polynomial, any other function that only depends on the present input. So memory and memoryless. Another characteristic of systems is linear or not linear or nonlinear. So we're definitely in favor of linear systems most of the time, but certain types of operators that you use in DSP are nonlinear. And a good example might be squaring, which would be leading up to the estimation of power in a signal or energy in a signal. Absolute value is used in statistical processing too, or other things that you might do that are nonlinear. But a linear operator says that superposition holds, which says in words here, the present output can be formed as a linear combination of the inputs. And this has to hold for the entire time axis and has to hold for any constant values that you want to apply, A and B. Obviously, to have this make sense, these are finite. They're not infinite values of constants, but so that it can hold for any value. And because I stand up for too long, my hip gets messed up on one side if I'm not standing level. So if I was outside, I'd be stretching my muscle there. So there's different techniques for proving this. When you have to show this for a problem, you generally take two approaches. One approach is if you think it's linear, you go about showing that superposition holds by going through a general case example. If you think the system is nonlinear, you just have to come up with one counterexample. So you plug in one set of numbers and just show that, hey, linearity doesn't hold. And that's, I'm going to probably take a look at some examples here in a bit. If I'm thinking the way I have the notes set up here. The generalization of linearity is to take any number of inputs and do superposition with them. Okay, so let's just back up here. Memoryless. There's 5 properties I need to go through, so I'm just counting up to make sure I know where I'm at with going through the properties. Third property, time invariant or shift invariant. So time invariance in words here means that if I take an input and shift it by n-naught samples, I get the same output that I would get with the unshifted input except with the shift factor. And I know it's very easy if you're tired or just not wanting to engage your brain completely to think, what did you just say? It doesn't seem like you did anything, right? You can look at that and say, the math there doesn't, it looks like you're stating the obvious. But I want you to think about the physics and always come back to the physical aspects of it, whether it be an analog circuit design with RLC and networks or whether it's an algorithm on the computer. The idea of the time invariant means that the network, the analog circuit or the algorithm, the properties of them do not change with time. I put them into service at 6 a.m. in the morning, and at 12 noon, when the sun is beat down on that algorithm or the electronics, it still behaves the same. Nothing has changed in terms of the algorithm or the components. If it's an electronic circuit, temperature is just a bad thing for electronics, right? It makes things change. So it's probably not time invariant, strictly speaking, although it might be very small variation due to temperature, especially if the temperature is constant, like it's a cloudy day or something like that. In an algorithm, time invariance is pretty much the norm. But if you write your algorithm so some attribute of the system is going to change, like a gain or a coefficient in a filter is going to change, like an adaptive filter, which is purposefully made to be adaptive, then it's not going to be time invariant anymore. So you just have to look to see, is something changing with time? And that's generally pretty easy to see. I mean, I'll just that looks cool. A is just a constant, but now you've got a constant that's changing with time, n. It's changing with the time index n. So that's going to be time varying. Okay, so that's 3. Okay, this is 4. That'll be 5. So 4, causality, or non-anticipative. If all values, if all output values, say y at time n naught, depend only on input values x of n at n less than or equal to n naught, then the system's output only depends on past and present input values, and that means it's causal or non-anticipative. Real-world systems are always going to be causal. If we could predict the future, there'd be people trying to sell you all kinds of things. There'd be, I'll just take an example of like dictators, like I'll just think of Putin as an example since he's kind of in the news a lot, and I have my thoughts about what's driving him to do what he's doing. I'm not going to share those thoughts, but you can have your own thoughts. He'd be really happy if he could see the future because he'd know exactly what to do to help guide himself towards that objective or whatever. Just like an investment advisor would say, buy this stock because I know this one's going to be big in 2 more days' time, and then he'd also say, and sell the day after that or something like that. And you'd say, if I knew that, I wouldn't even have to talk to you because I'd know exactly what to do. But at any rate, in signals and systems, we can build a predictor, and we do build things that predict the future, but they only predict the future based on the present and the past. Does that sound okay? I mean, it's fair to build something that predicts 1 step into the future, 2 steps into the future. I worked on a project that was working on adaptive data rate communications, and that was the big challenge. My boss had a patent on adaptive data rate, something where you shift gears as you drive into an urban canyon or something where the propagation gets to be challenging or there's lots of interference. And the idea was to predict the channel so that you could downshift the data rate to still maintain reliable communication but not have as much bandwidth. I mean, Wi-Fi does that, cellular does that to this day, but predicting the channel so that you could anticipate, I better downshift the data rate before it actually gets tough. That was what it was all about. I mean, Wi-Fi, it does that in our house, right? When we're close to the Wi-Fi base station, we get maximum throughput from our base station. If we move further away, in the microwave oven in my house, when the microwave oven turns on, it interferes with the Wi-Fi and things drop off drastically. It almost dies at times. And I've got a theory about that. So actually, related to that is cognitive radio, which is the idea that a radio system can predict and reuse channel that another user is not using. So cognitive radio is having an intelligent radio system where I'm going to use your bandwidth even though you're paying for it. I know you don't use it all the time, and I'm going to be really, really good about getting off the air whenever you're using your channel. And that's one of the foundations of cognitive radio that came along well over 10 years ago. Has anybody ever heard of cognitive radio? Okay. It's a really cool idea, but people that own spectrum have to be willing to share it, and people that pay money for something generally will say, I'm not sharing unless you're going to help pay for it. So there's still confusion out there, but cognitive radio ideas are used in our wireless routers right now. You set up a router in your house. In the beginning, you had to give it a Wi-Fi channel, and you had to know what channel to pick. And how did you even know what channel to pick? Well, in the beginning, for me, nobody in my neighborhood had Wi-Fi, so I just picked a channel and it worked. But nowadays, you go and you look in your laptop or cell phone and see how many Wi-Fi stations there are, and it's like, I don't even know how to pick a channel because there's so many of them. So there's algorithms now on wireless routers that help pick your channel. I contend, though, that in my neighborhood, my neighbors have picked all the frequencies that are free of microwave oven interference, and I'm stuck with the frequency that my oven happens to use. So I'm kind of out of luck or whatever. If I wanted to change to a different frequency, I'd be on a neighbor's frequency. I just have this feeling, because I brought home a spectrum analyzer and I verified that I'm just right dead on the microwave oven frequency. But
or if their router is adaptive, set yours to one of their channels, turn your power all the way up and make their shift.
yeah, well, I've heard people having discussions on the driveway between their neighbor about blah, 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 this with that. Has anybody ever thought about that, though, or has this ever been an issue for anybody? It just shows you that, you know, we have to share, we have to get along, we have to coexist, a lot of other things. But as an engineer, I mean, we think about that. My neighbors, I don't believe, think about that because they're not thinking about electrical engineering. So my wife, who's also an engineer, says I obsess over things. Have you ever been charged with being obsessive? It's pretty easy to happen. Okay, so I got sidetracked on that for a variety of reasons. I was talking about cognitive radio and things of that sort. So non-anticipative, we don't know. We just have to work with present and past. So you study the problem, and I'll pick some examples here in a bit. Last of the 5, bounded input, bounded output. So there's an acronym that's you can pronounce BIBO, if you want to call it that, bounded input, bounded output. And that just says your bounded input, bounded output stable if and only if every bounded input produces a bounded output. So this is a famous mathematical term. If, well, I didn't outline that properly. I'll do this. Mathematicians love to use that term when they're talking about properties of some mathematical whatever. So they'll do a proof, and the proof, if it's an if and only if condition, it's a much stronger statement than if this, then that, if that, then this, is what we're saying with if and only if. They go backwards and forwards. So this is true, that's true. If that's true, then this is true. So that's what the if and only if means. So interpreting it would say a system is stable if every bounded input produces a bounded output. A system where I observe that every bounded input produces a bounded output is stable. So I'm just saying they go back and forth. So technically what you have to do is establish, though, that a bounded input, something whose magnitude is less than a constant, which is less than infinity, that if you stick that into the system of interest, it will ensure that the magnitude of the output also stays bounded or less than some constant, Vy, that's less than infinity. So really simple example. My pen turned off here. Reset the Bluetooth. So technically speaking, this system, which is a memoryless system also, is bounded, is BIBO stable only if requires what? What's going to have to be required about this system to make sure that it's bounded output? Well, we can figure that out. We can say that can have that, and then I can say the absolute value of yn So what's required to make sure that the output is less than infinity? I know Bx is less than infinity, so what do I have to just simply add on this to make sure it's stable? I just have to add on there that the magnitude of A has to be less than infinity. I mean, I went one step beyond talking about it being stable. I talked about what do I have to do in the system to make sure it's stable. In this case, I just have to make sure magnitude of A is less than infinity. If you're wanting to prove that a system is not stable, it's probably easier to come up with a counterexample. And that counterexample would be to just establish that there's one particular bounded input which produces an unbounded output. So an example I'm going to think of there would be, I mean, a mechanical example that you've probably heard about before is the Tacoma Narrows Bridge. Remember that example? 3 years ago, when my family and I went to Seattle and Portland, we also went to Bremerton. We stayed in Bremerton, which is across the bay in Seattle. So we could take the ferry to go to downtown area rather than have to drive and park. So we actually stayed over there to make it a little bit more exciting. But I didn't realize till we were driving to Bremerton that we had to go across that bridge. So when that bridge name came up in front of me, and it's a toll bridge too, I didn't realize that either, and I didn't have any toll money at first, but I didn't realize that's the famous bridge that blew down in the wind shear. So that was a system that was stable, but then under the wind shearing action, it hit a resonance and it caused it to go unstable. And for us in signals and systems, if we have a system that's marginally stable, we might, and we'll run into this in the next chapter, we might have a pole at z is equal to 1, so it's right on the unit circle, and if a second pole hits that system, namely due to the input from an impulse response, it will change the system's output. The response to an input might be something like this, a step, but if we hit the input with another step rather than a delta, then the output's going to, pen is disconnecting here, then it's going to ramp up like that. It's going to go unstable. So that's those things. And I know those of you that had Dr. Trimboli, being that he's a control person, he'd be very big on that sort of thing, like marginally stable is just not safety good, because you know that there's something that can hit it and it's going to explode. You don't want that to happen right while you're driving your car. It's like having a wheel fall off or something. Actually, you don't want to think about anything. A lot of things that we use every day, we don't want to think about what happens if that breaks while I'm in motion. It just gives you a shuddering feeling like what could happen. But okay, we're going to run out of time here. We have 10 minutes left. I want to get through a couple of examples, but we do have next Wednesday, before the homework is due, to have more discussion. So in at least a minute or so, can anybody give me any feedback on something they'd like to have me for sure talk about in the homework right now? I will be posting the hints, but is there some problem you want me to talk about? The next two examples that I have in that Jupyter notebook are related to linear time invariant systems, so I really can't go through those examples without first going through this. But is there something else in a homework problem that I could jump over to you? rather than just going through this for 10 minutes before we quit. Just giving you the opportunity. If there's another homework problem that has something in it, because there are problems involving the 5 properties. I know that. I'll gladly go over anything next week on any of that stuff, or do more examples. I think right now I'd just like to get through this so I can say that you can use that to help you look at other problems. I'd like to get through as much so that you can do as much exploring of the problems before we meet again, and that way you'll have more questions. One of the things that I know happens is if you don't have reason to study your homework problems, you don't know what problems you've got, right? You just don't know what is out there to cause you a harmful feeling like, I don't know how to do that. So I got to give you some reason to want to look at things, and I definitely want you to have looked at the problems before next Wednesday, because that's how I can help you right here and now, rather than the night before all of a sudden I'm getting Slack messages. But also understand we can do Slack, we can do voice on Slack. So where I'm working at right now, they told me both projects I've been helping with, I'm supposed to take my hours down to about 0. So now I'm going to be not doing as much. I'm probably going to come over to campus, I think, and start cleaning up my office. That's an unpleasant thing, but I've got to get started on it. So I'm thinking that's probably a good thing to do, just start doing something. And you guys are going to benefit a lot from that. I know I'm rambling a lot, but I have a lot of books in my office, and I can't keep them all, and I'm going to start giving a lot of books away. So I'm probably going to, if you guys are interested in getting anything, I've got some special books that I'm going to give away to whoever gets the highest score on an exam, and some other things. I mean, I've already got some things in my head, but I'm going to have stuff that you're the only real class that I have, so I'm going to give you some opportunity to get some things that might be of interest to you. Just the way it works. Dr. Zemer left. I took some of his books. I'm going to now give some of his books away because I haven't used them since I took them. I mean, no guarantees that you'll ever even open the book, but you might have a use for it. So we're going to move on to LTI systems, linear, end time invariant. So those are 2 of the 5 properties we just talked about. They turn out to be the systems with which we're the most interested in. So LTI is the most important type of system. So before we discuss LTI, we first talk about the property of a system called its impulse response. And that is going to be it's going to be the response h of n when x of n is delta n and the system is at rest. So I think of the impulse response as being the signature of the system. And for me, it'd be like taking my bottle here and having some sort of a sensor around my bottle measuring the vibration and just pinging it with my finger, just giving it a single ping, which is like a delta. What sort of ringing action happens on the circumference of that cylinder? There'd be some vibrations that get set off. So that's the impulse response. That's one type of characterization. We could use a step, we could use a burst of a sinusoid, we could use all kinds of different types of stimulus to get some characterization for our system or signature, but delta is the simplest. So it's the one that brings nice results. And now remember that for any system we can write the x of n as a linear combination of sample values of the input and time-shifted deltas. So the game we play now is we say let's apply an operator around that x of n and expand that x of n using that sum formula. And so that gives you this line right here where you have the sum over all the values of the input as weights, x of k, and then time-shifted deltas. And now we invoke linearity, and linearity would say that the response to a linear combination of inputs could also be written as the linear combination of the individual responses. So what that does is it's saying I can take this T, my pen is acting up badly, it keeps disconnecting. So I can drive it right inside of there. I can change the order of the operator and the superpositioning operation, because that's what linearity allows you to do. And a special case of linearity that I always think about, I use that in my Signals and Systems for Dummies book actually, is the karaoke machine. I don't do karaoke, I do play in the jazz band. I had a really nice concert last Thursday night that I invited you all to, but you probably didn't see it on the website or didn't want to go listen to some live music over in Manitou. But what is a property of a karaoke machine that you know can definitely be bad? The music's playing and you're supposed to come up and sing into the microphone, right? That's the principle of the karaoke idea. But if the amplifier is not powerful enough, the person starts singing really, really loud, and what happens? Their voice gets all distorted and all ugly sounding because they've overdriven the system. That is not a linear system. A linear system says it doesn't matter how big and powerful that person's voice is, they're just going to blast out of the speaker and it's going to be loud and deafening, but linearity is holding. And that's what this is. It's saying I can interchange the orders there, and I can just have T operate around the system, the time varying input. The x of k, in terms of this sum, I wish this would stay connected for me. That's a constant. And linearity says constants can come outside of the operators too, because they don't alter the net effect if it's a linear system. So T just gets to operate on the delta, the time varying piece, and that produces the impulse response. And it produces the impulse response with a time shift because of the assumption of time invariance. The fact that I'm going to apply that delta to the system at a different time, but it's still going to behave and produce the exact same shape. It will be shifted in time, but it will not get bigger or smaller. It will just shift in time. So then that produces then these two equations, which are just, you know, what we have right here. It's this. This thing is just, that's one form of the convolution sum, and then it's just changing the orders, but that's the infamous convolution sum formula, which says that the output is the convolution of the input and the impulse response of the system, and that forms a very fundamental way of calculating systems outputs given their signature impulse response. It also provides challenges in terms of calculating convolutions, which is just a procedure that is kind of ugly to have to follow. So I have a nice example of that in here, of going through a problem, and that's what you have to do in the homework problem. So since the time is up right now, I'm just going to jump back over here and see if I can get this a little bit bigger. My mouse is not cooperating with me. But you have to convolve two signals. So here you have to convolve a u of n with an a to the minus n u of minus n. So this provides a bit of a challenge. There's a nice example in the notes, but this provides more of a challenge because of the fact that one sequence is going off to the right, the other sequence is going off to the left, and then you have to flip one of them, then you have to slide it, and then you just have to go through the mechanics of doing that. So that's what you have to figure out how to do, and I'll talk about that some next week. The simulation of that, though, is all in here, and it's all well and fine. Those are the the two waveforms that you have to convolve, and then I use a function in my module SIGSYS, and it produces that for the response. And this is a mind-boggling thing, because a system that has an impulse response that runs in the negative direction is not an analog system you can relate to. It's not an RC filter, because that's a causal filter. This is an anti-causal low-pass filter, and you're not used to seeing an output that would behave like that, because you're not used to a system that would be anti-causal. But in DSP, you have this total flexibility to just define something that way. So the math behind this is a little bit more involved, and we'll jump back over when we look at this. We will be reviewing here the geometric series to get the closed form solution. We're going to use geometric series a lot in this class the entire semester, and it gets used in so many different ways. It's something that I know in calculus you learned about when you were studying sequences and series. Remember the geometric series formula? It gets used here for so many things. You're going to have it loaded back in your memory bank. I absolutely guarantee it. You're going to get it back, and you're going to also find some helpful pages here on the website. If you feel so inclined, click this link. This takes you into the back side of my website, and you can see a lot of different things you're going to be grabbing onto eventually, but one of them is the Exam 1 Tables PDF. So you'll have this by your side when you take your first exam. Notice there's a bunch of sum formulas right in here. So I do care about this stuff, and you'll be learning how to use these formulas. So
Can you show where that link was again?
yeah. This is the back side of my website. It's just telling you what the documents look like, but to get to it, just other course materials. Okay, I'm going to stop the video. You can ask me questions while I'm tearing down if you want to, or we'll be up in lab shortly.